Welcome everyone. Welcome to this lecture of analysis of RL, RC and RLC series circuits. So let us first, before starting this, in this module, the excerpts has been taken from the Basic Electrical and Electronics Engineering book written by Prathamesh Das and Maitreyi Kanjilal. So first we will consider series RL circuit. So let us consider a resistance R and this inductance L. They are connected in series, okay, and we are applying a AC voltage source. And this V is the RMS value of the applied voltage VR, which is the voltage drop across this resistance, and this VR is the RMS value. This VL is the RMS value of the voltage drop across this inductor L, okay, and I, which is the RMS value of the current that is flowing through the circuit, and VR equals to IR in phase with the current, because we know for a resistive circuit voltage and current, they are in phase. Now this is VR is equal to IR. This is for the resistor part. What for the inductor part? What is the voltage drop across the inductor? VL equals to I into multiplied by the inductive reactance, okay, which is I into XL. XL means omega L. I into omega L. And we know for a inductive circuit, the voltage leads the current by an angle of pi by 2 radian, that is 90 degree, okay. So if we draw this situation in a voltage triangle, so what we can observe is, because if I want to draw for an inductive circuit, the voltage leads the current by an angle 90 degree. So if this is my current and this is my voltage, inductive voltage, the angle between them should be 90 degree. And here voltage and current, they are in phase for a resistive circuit. And this vector V is the resultant vector. So this triangle is called the voltage triangle. Now, if I want, this side is my VR and this side is my VL. This is my resultant vector. If I consider this resultant vector, it is also leading the current by an angle phi, okay. So, if I want to perform the phasor sum of this VL and this VR, so resultant vector V will be equals to square root of VR square plus VL square. VR means IR whole square plus IXL. VL is IXL whole square. So if I take I out of the square root, I will get root over of R square plus XL square. So let us take as Z. And Z is nothing but the impedance of the circuit, which combines both this resistance and this inductance, okay. And XL, that we have already considered omega L. Omega is 2 pi F into L, okay. Now from this phasor diagram in this figure, we see that this current, it lags this resultant applied voltage by an angle of phi. So tan phi will be VL. If this is VL, this will also be VL, right? So tan phi will be VL divided by VR. VL means IXL, VR means IR. So it is XL by R, okay. So if I know XL and R value, I can easily calculate the phi, okay. And we have considered this I current is the RMS value of the current flowing through the circuit, okay. Now if I consider the instantaneous, because this is an AC voltage, RMS value we are applying, right? RMS value of the applied voltage. So at any instant, if I consider the current flowing through the circuit, which is also called the instantaneous current, that can be written as I equals to Im sine omega t minus phi. Why my omega t minus phi? Because in this circuit, the current is lagging behind this voltage by an angle phi. That is why Im sin omega t minus phi. Im is a peak value of the current, where phi, just now we have found phi equals to tan inverse of XL by R. Now, so from this equation V equals to, we got Iz, right? Where Z we have considered root over of R square plus XL square. Okay, or Z square we can write R square plus XL square. So previous triangle was my voltage triangle. Similarly, if I plot an impedance triangle, then this side will be my Z, this side will be my XL, and this side will be my R, right? So this is my impedance triangle. This is my Z, this is my XL, and this is my R. Okay, so this is the right angle triangle where the base AB is R, side BC is XL, the hypotenuse AC will be root over of R square plus XL square, which is Z. Okay, and this angle is called the impedance triangle, and the angle between these Z and R is a phase angle of the circuit, where cos phi is R by Z. This cos phi is R by Z is known as the power factor of the circuit. So if I want to calculate the power in the series RL circuit, how we will calculate? Okay, so we have previously seen the voltage triangle, the phasor diagram of the voltage triangle. We have seen the phasor diagram of the impedance triangle, and since it is an RL circuit, so what we have seen, the for the resistor part, the voltage and the current, they are in phase. Okay, but if for a purely inductive circuit, what we know, the voltage leads the current by an angle 90 degree, and the resultant vector here, that is leading the current by an angle phi. Okay, so if at any instant, if I consider the instantaneous value of the applied voltage, V is Vm sin omega t. So I will be Im sin omega t minus phi, because that we have already seen here, right? Because this current is lagging behind this voltage by an angle phi, right? Now, so what will be my instantaneous power? Power P equals to simply the multiplication of Vi, which is Vm sin omega t multiplied by Im sin omega t minus phi. Now, we will just make it, divide it by 2, multiply it by 2, so that we can put it in a form of 2 sin A sin B. We know 2 sin A sin B means cos A minus B minus cos A plus B. So, we will get this form. Okay. Now, this notice here, this cos 2 omega t minus phi, it is nothing but a periodic function. And we know the average value of a periodic function over a complete cycle is 0. So, this term will get cancelled out. So, the average power of the circuit will remain only as half Vm Im multiplied by this cos phi. And we know how do we calculate the RMS voltage? RMS voltage V equals to Vm by root 2, and RMS current I equals to Im by root 2. So how will you calculate the power? Power P equals to this Vm by root 2 multiplied by Im by root 2 into cos phi. So this is nothing but the Vi cos phi, where this V and I are the RMS value. Okay. Now we can calculate the power consumed by the circuit by other method also, because power consumed by the inductance is 0. If you calculate the power consumed by the inductance, then you will obtain a term of sine 2 omega t. So if we take, it is also a periodic function. So if we take the average value of this periodic function over a complete cycle, so that term will also get cancelled out. So that power consumed by that inductive element will be 0. So in this series RL circuit, the power consumed will be only equals to the power consumed by the resistive element. So that is equals to I square R. We can write it as I into IR. So I means V by Z. multiplied by IR. So VI into R by Z. R by Z, what we got? R by Z is nothing but the cos phi, which is the power factor of the circuit. So we can write it as V cos phi equals to R by Z. So it is VI cos phi. Okay. Now, see here, previously we have seen the voltage triangle, we have seen the impedance triangle, right? Now, since it is a series RL circuit, so in series RL circuit, what happens? In series RL circuit, this voltage is leading the current by an angle phi. That's what we have seen, right? Or current in from this triangle. So, or current lags the voltage V by an angle phi. Okay. Now, if this angle is phi, this will be I cos phi and this will be my I sin phi. Okay. Now, there are three terms of the power. Okay. One is called the apparent power, one is called the true power, one is called the reactive power. So, we will see each one of these one by one. So, the product term of the RMS value of the voltage and current, that is VI, that we have seen in the previous slide, it is called the apparent power and it is measured in volt ampere, VA or kilovolt ampere, and it is denoted by this capital letter S. Okay. Now, from this figure, we can easily understand this current is lagging behind the voltage by this angle phi. Okay. Now, if it is phi, it will be I cos phi, I sin phi, that I have already told. Now, for the resistive element, the power consumed by this resistor R, let's say it is PR. So, that we have already calculated in the last slide. What was the power consumed by the resistor? It is VI cos phi. We can also write it as I square R. Okay. So, for the resistive element, this I square R power or this PR is called the true power. And for this resistive element, the reactive power or the inductive power will be 0, right? So, the total true power will always be the power consumed by the resistive element in your circuit, which is this active power plus reactive power, or in this case it is inductive power. So, it is only PR, which is VI cos phi. Next, we also have to calculate the power consumed by the inductive element. So, for power consumed by the inductive element, the active power or real power will be 0 and the reactive power will be QL will be equals to VI sin phi. We can also write it as this part is my the reactive power. Okay, this part is my reactive power. So, this is VI sin phi and we can also write it as I square XL, similar to I square R. So, it is I square XL. XL is the inductive reactance. Okay, so if we draw these power triangle, if we draw this power triangle, so this is my base is my true power, here it is my reactive power and this is my apparent power. Okay, so if apparent power, this is S, this is my true power which is in kilowatt, apparent power it is in kVA or kilovolt ampere, and this power, reactive power, it is in kVAR or kilovolt ampere reactive. So, S square will be, this is P square plus Q square. P means VI cos phi, that whole square, and Q means VI sin phi, that whole square. So, S square will be my P square plus Q square. Okay. So, this is my power triangle. This is my power triangle. Okay. Because this side, if you look from this rectangle, this side is my what? This side is my VI cos phi. This side is my VI cos phi true power. This side is my VI sin phi. And this is my resultant vector, which is the apparent power. Okay. Next, we will move on to the power factor. So power factor means the ratio of true power and apparent power. What is true power? It is P, apparent power S. P means this power consumed by the resistive component, which is Vi cos phi, and this apparent power is simply the product of these RMS values of this voltage and the current, right, that we have already seen. So it will be cos phi, which is the power factor. So from here we get three definitions of power factor. So it is a cosine of the phase angle between the voltage and the current. Then ratio of the resistance to impedance. We have seen one relation cos phi equals to R by Z, right? And another definition of power factor can be the ratio of true power to the apparent power. Okay. Next, we will move on to the series RC circuit. So, in the series RC circuit, we will be having a capacitor connected in series in the circuit. So, same as the previous case, this supply voltage V is the RMS value. This VR, which is the voltage drop across this resistive component, and VR is the RMS value. Voltage drop across this capacitive component is a VC. It is also an RMS value, and I is a current flowing through the circuit, which is also an RMS value. Okay. Now, if we draw the voltage triangle, how we will draw? See, this is the voltage. If we draw the voltage VR and the current I, they are in phase. If it in a resistive element, voltage and current in phase. But in a capacitive element, what happens? The current I, it will lead the voltage VC by an angle of pi by 2 radian or 90 degree. So, if this is VC, if this is VR, we can take the resultant vector in this direction. So, this is my resultant voltage, and these resultant voltage, it also lags the current by I by an angle of phi. Okay. Now, obviously, as you can see in the figure, pi is less than pi by 2. So, if we do the phasor sum, so V square will be VR square plus VC square, or V equals to root over VR square plus VC square. Now, VR, we know this is IR, and VC will be I into XC. Okay. So, if we put these VR and VC values, we will come up with V equals to I into Z, where Z equals to root over of R square plus XC square. Now, these applied voltage V, it lags behind this current by an angle of phi. So, tan phi will be, if this is the angle phi, tan phi will be my VC by VR. Okay, VC means IXC and VR is IR. So, II will get cancelled, it is XC by R, or XC by R means we can write it as XC means 1 by omega C, so it will be 1 by omega RC. Okay. Now from here we can draw the impedance triangle. This is my resistance, this part is my capacitive reactance, and this part is my impedance. This is my voltage triangle, this is my impedance triangle. So cos phi will be R divided by Z. Okay, so if we consider the instantaneous value of this voltage V is Vm sin omega t, so the instantaneous value of the current will be Im sin omega t plus phi, because the current now it is leading, current is now leading the voltage, okay, leading this voltage V by an angle of phi. Now, so for that, if we now calculate the power in the series RC circuit, how will you calculate? So for that, we have to calculate the power across the resistive element, then we have to calculate the power across the capacitive element. So for the resistive element, the true power or active power will be PR equals to VI cos phi, which is nothing but the I square R, and the reactive power consumed by these resistive element will be 0. And for the capacitive element, the active power will be 0 and the reactive power QC will be minus VI sin phi. Because in an inductive circuit, the reactive power is positive, but in a capacitive circuit the reactive power is negative, so it is, that is why minus. Okay, so we can also write it as minus I square Xc, similar to I square R. So total active power consumed by is Vi cos phi, that is offered by this resistive element, and total, which is in watt or kilowatt, and total reactive power consumed is by the capacitive element, which is mod, we can take it mod Vi sin phi, which is in volt ampere reactive. So the, if we draw, this is my power triangle, this is my resistive power, this is my reactive power, and this is my apparent power. So A's apparent power, we have seen it is calculated by the multiplication of the RMS value of voltage and current. So A's, from this triangle we can write it as root over P square plus Q square. And power factor, how do we calculate? It is calculated as, here only we have seen, right, how to calculate. It is true power by apparent power. So it will be, true power is Vi cos phi, apparent power is Vi. So true power unit is in watt and apparent power, its unit is in volt ampere. Next, if we see the series RLC circuit, so now we will have all the resistive, inductive and capacitive component in my circuit. Okay, so these VR is the RMS value of the voltage drop across the resistance R. VL is the RMS value of the voltage drop across this inductor L, and VC is the RMS value of the voltage drop across this capacitor, and I is the RMS value of the current flowing through this circuit. So if you want to draw the phasor diagram, how will you draw? Since, so VR and I will be in phase. For a resistive element, we know current and voltage, they are in phase, and for a inductive element, the voltage leads the current by an angle 90 degree. So if you consider that your inductive reactance is higher than the capacitive reactance, or VL is greater than VC, then how will you draw? VL is greater than VC. So this part VL, we can draw it, VL leads the angle by a 90 degree, and so this is my VL vector and this is my VC vector. Okay, this is my voltage drop across the capacitor. So this is my resultant vector, which is making an angle phi with this current. Okay, now if we consider that inductive reactance XL is less than the capacitive reactance XC, that means my VL will be less than VC. So in this case, this will remain fixed. That means voltage drop across the resistor and this resistive element, voltage and current, they are in phase. Okay, so in an inductive element, we know the voltage leads the current. So this is my voltage, and opposite side we will be having this this part will be having my VC. Okay, voltage drop across the capacitive element. So this will be my VC minus VL, because here we have considered that is XL is less than XC. So this will be my resultant vector now, which is making an angle phi with this current I. So for our calculation here, so for this case, when you consider VL is greater than VC, your resultant vector V will be we have considered is here VL is greater than VC. So for here the resultant vector V will be root over of VR square plus VL minus VC whole square. Now if you consider this one where VL is less than VC, so here the resultant vector V will be root over of VR square plus this one VC minus VL whole square. So for our calculation, we will consider that is VL greater than VC. That means this diagram, first diagram. Okay, so and at that time, what is the resultant vector we got? Root over of VR square plus VL minus VC whole square, where R is the resistance of the circuit, XL is the inductive reactance, and XC is the capacitive reactance. XL is omega L and XC is 1 by omega C. So we know all these VR, VL and VC value, right? VR is IR, VL is I into XL, VC is I into XC. Okay. So now if we put these values in this equation, we can get V equals to, if you take I out of the square root, we will get root over of R square plus XL minus XC whole square. So I will be this V by this term. So V by Z, where Z is my impedance of the circuit and it is equals to root over of R square plus XL minus XC whole square. So if you now draw these impedance triangle, so this part is my resistor, this part is my XL minus XC, and this part will be my impedance Z, right? So if this is angle phi, then tan phi will be XL minus XC divided by R, and the power factor of the circuit, we know cos phi equals to R by Z, R divided by Z, we have already calculated the Z, okay? Now, so the resistive element, power consumed by the resistive element is the true power or active power. It cannot consume any reactive power. So PR will be VI cos phi or I square R. Reactive power consumed by the resistive component is 0. Inductive element, what you do? It can't consume any active power or real power. It will only consume the reactive power. So the power consumed by the inductive element QL will be I square XL, and the capacitive element also, it can't consume any real power or active power, but it will absorb only the reactive power. So here QC will be minus I square XC, since as I told, the inductive power, capacitive power across the inductive element is positive and the power across the capacitive element is always negative. So if you add all this power, so now you will get here across this resistive element, what you will get? Across this resistive element, we will have only the active power or true power, which is VI cos phi or I square R watts, and total reactive power, which is consumed by the inductor and the capacitor, which is my VI sin phi. Or if you put the value, it is I square into XL minus XC into VAR. So the apparent power, we can same process like the previous two cases. If we draw the power triangle, apparent power S will be equals to root over of P square plus Q square. We know the value of this P, which is I square R. We know the value of this Q, which is this component. So after calculation, we will get I square into Z, and the power factor cos phi is R by Z. R is nothing but, so if we multiply both numerator and denominator by I square, then it is give us I square R is my active power or true power, and I square Z is nothing but my apparent power. So that's what the definition of the power factor, right? The ratio of the true power to the apparent power.